The basic aircraft architecture of wings and canard with distributed propulsion has been a constant since the early days of Lilium. As the design details have evolved, so has our toolset. As well as utilising commercially available software, several in-house computational tools have also been developed to enable modelling of such things as aircraft and engine aerodynamics, flight control laws, environmental noise and structural loads, and many more besides. This type of analysis allows us to quickly iterate some of the finer details of our architecture. Computational analysis is even more powerful when calibrated and validated by testing. Some good examples include wind tunnel testing, where our simulations are matched by flight conditions in a closed environment. And of course, real-world flight tests. Our technology demonstrator, Phoenix, which has been flying since 2019, has been about proving out our architecture in real flight conditions. Recently, we also demonstrated transition and flow attachment on the main wing, where lift is generated by the wings rather than the engines. This is a significant step forward. It's the most difficult manoeuvre that a VTOL aircraft can undertake. Transforming the future of regional air mobility takes more than just innovative technology. You can build something new that flies, but can it be certified? You can build something that can be certified, but can it be built at scale? You can build something at scale, but can it be sold profitably to a real market? So this requires a very sober understanding of the certification process, which is precisely why we've brought on board some of the most proven technical leaders from the aerospace industry, who've delivered aircraft certification programs and therefore understand the rigour of this process deeply. Let me touch on some of Lilium's certification milestones and why they're important. The European Union Aviation Safety Agency, EASA, is a primary certification authority. We're also undertaking a concurrent cross-validation with the FAA. We have participated in several EASA and EUROK working groups, which has contributed to the publishing of SC-VTOL certification regulations in 2019. This allowed us to begin designing our aircraft. In 2020, we received our certification basis, the CRI A01, from EASA, allowing us to have confidence in the specific requirements that our aircraft would have to meet. In April of this year, we submitted a full set of certification means of compliance proposals, affirming the precise way in which we would demonstrate compliance with the safety standards. Lastly, the DOA, the Design Organisation Approval. We've now completed our second out of a planned 4 DOA audits, meaning that our engineering team is well on the way to being fully qualified by EASA to design and certify an aircraft. An aircraft cannot be certified and launched without strict adherence to this process from the beginning. Otherwise, you only have a prototype. Which is why we're excited to say that we've successfully conducted a rigorous preliminary design review process. We've converged on a final design, which we have every confidence safely achieves the performance our launch customers require. It is a package that can be successfully certified and can be profitably built at scale. Let's walk through where we ended up on a few of the most important design details. Let's start with one of our most iconic design features, our electric ducted fan engines. By simply increasing the diameter of the duct fans by a few %, we were able to reduce the number of engines and maintain the total thrust and efficiency required. This then allowed us to achieve a better aerodynamic balance between the main wing and the front canard. It also means a lower unit cost and a lower maintenance cost. And with the large diameter fans, we can use better acoustic damping in the jet ducts to minimise noise. With the change to 30 engines, we have kept the ratio of 3 engines to 1 battery pack. Therefore, the number of battery packs reduces from 12 to 10, but is sized to maintain the overall hover power density of approximately 2,500 watts per kilogram, but in a simplified and lighter weight packaging. We also made some subtle changes to our duct design and the fuselage. We've slightly shifted the main wings rearward and upward, and added winglets to the canard, in order to make the whole aircraft behave better and fly more efficiently. This leads to a cruise power density which is 1/10 of the hover power, and allows us to improve our range. We've added running landing capability, which is important to certification because it increases reserve range to address the jet's ability to deal with real-world scenarios and be able to divert to alternate landing site and perform a short-running landing, which gives us the ability to use more cell energy than is otherwise accessible in a normal vertical landing. We also believe that such a capability, while rarely used, will provide additional reassurance to our customers. Further, in terms of operational safety, our 30 engines, large number of flaps, independent battery units, and multiple flight control computers provide us with significant redundancy. We are on track to meet the extremely high 10⁻⁹ safety standards. This means the probability of a catastrophic failure is less than or equal to 1 in 1 billion flight hours, as set by EASA for commercial aircraft and for eVTOL. Our battery team has been evaluating dozens of candidate cells over the last several years. We have now picked a very capable cell design, designed by Zen Labs and manufactured by Custom Cells, that we believe provides us with excellent power density as well as energy density. The battery is exclusive to Lilium within our target market, and we believe it could be one of the highest performance cells that is practical for eVTOL in existence today. The advantage of the Zen Labs cell is its combination of both superior specific energy and specific power capabilities. When compared to commercially available state-of-the-art cells, the Zen Labs cell surpasses both the specific power capability of the high-power cell and the specific energy capability of the high-energy cell. It's critical to note that based on these independent test results from Energy Assurance, the cell is able to support a high specific power of 2,500 watts per kilogram, even down to 20% state of charge. So, when we tie all these design elements together, we remain on track to meet our previously stated physical range of approximately 250 kilometers or 155 miles, using a short vertical takeoff and landing at operational empty weight. This equates to a projected operational range of approximately 175 kilometers, assuming a vertical takeoff at maximum takeoff weight and a vertical landing, 45 seconds duration, such that 20% state of charge remains following the landing. It's worth mentioning some important points here, since these calculations are often misinterpreted. We use conservative vertical hover phase assumptions in our calculations. This range doesn't account for the additional 20% energy accessible for reserves thanks to the rolling landing, which would be supplemental to these figures. Lilium Ultimate Operating Range will account for these reserves as well as other certification requirements, and will be confirmed between now and our entry into service. We believe we've converged on an optimum final jet architecture that will meet the agreed certification requirements and achieve a projected physical range of approximately 250 kilometers at launch, which is more than enough for our anticipated launch routes. As battery technology and performance improves, we will be able to upgrade the aircraft with newer batteries and offer even longer range to our customers.